Bismillahirrahmanirrahim. Last time we discussed about synaptic transmission. Just to sum up the events during this transmission, when nerve impulse reaches the synapse, there is release of neurotransmitter, which is excitatory, and this neurotransmitter, it binds with the inotropic type of receptors, and this results into opening of cation channels. There is sodium influx, and there is localized change in the membrane potential, and this is called excitatory postsynaptic membrane potential, EPSP, or excitatory postsynaptic membrane potential. Resting membrane potential in the cell body of the neuron is minus 65 millivolt. It is minus 65 millivolt. Now, because of EPSP, which resembles EPP, end plate potential in neuromuscular transmission. So because of EPSP, when the membrane potential reaches to minus 45, which is the threshold of excitation. So at minus 45 millivolt, there is discharge of action potential along the nerve fiber. So minus 45 is the threshold of excitation. And what is the purpose of EPSP? The purpose of EPSP is to bring the membrane potential from the resting value of minus 65 millivolt to the threshold of excitation, that is minus 45 millivolt. So the purpose of EPSP is to bring the membrane potential from normal value of minus 65 millivolt, resting value of minus 65 millivolt, to minus 45 millivolt, which is the threshold of excitation. At this potential value, there is discharge of action potential, a nerve impulse from the postsynaptic neuron. So this is the EPSP and the excitation of the postsynaptic neuron. Now, in some cases, there is inhibition of postsynaptic neuron. Action potential reaches the synaptic knob. Release of inhibitory type of neurotransmitter. It binds with the inotropic type of receptors, and there is opening of potassium channels and chloride channels. So binding of inhibitory neurotransmitter with the inotropic type of receptor, opening of potassium channel and chloride channel. There is potassium efflux and chloride influx, and this results into more negative membrane potential in the postsynaptic neuron. More negative membrane potential in the postsynaptic neuron. Normally, the resting value is minus 65. It becomes minus 70, more negative. And this is called hyperpolarization. So postsynaptic neuron becomes inhibited. And that is through IPSP. That is inhibitory postsynaptic membrane potential. So IPSP is inhibitory postsynaptic membrane potential. That is, the membrane potential becomes more negative than the resting value, and this results into inhibition of the postsynaptic neuron, and this is called IPSP, inhibitory postsynaptic membrane potential. I also mentioned last time, there is also presynaptic inhibition, in which the presynaptic node become inhibited. Right? I told you that in presynaptic inhibition, the neurotransmitter is GABA, gamma aminobutyric acid. Right? And in postsynaptic inhibition, the neurotransmitter is glycine. So glycine is neurotransmitter in postsynaptic inhibition, while GABA is the neurotransmitter in presynaptic inhibition. Now I've discussed properties of synaptic transmission. Properties of synaptic transmission. The first property is Dale's law. D-A-L-E. Dale's law. Dale's law is that at a given synapse, only one type of neurotransmitter is released, excitatory or inhibitory. At a given synapse, only one type of neurotransmitter is released. It may be excitatory or inhibitory. The second property is principle of forward conduction. Principle of forward conduction. That is, nerve impulse is always conducted from presynaptic knobs or terminals to subsequent neurons. So nerve impulse is always conducted from synaptic knob or presynaptic knobs to subsequent neurons, not in the reverse direction. Not in the reverse direction, always conducted from the synaptic knob or presynaptic terminals to the postsynaptic or subsequent neurons, not in the reverse direction. This is the principle of forward conduction. The next property is fatigue of synaptic transmission. Fatigue of synaptic transmission. When nerve impulses are transmitted repeatedly through an excitatory synapse. So when nerve impulses are transmitted repeatedly through an excitatory synapse, after some time, discharge of impulses from postsynaptic neuron decreases. So after some time, discharge of impulses from postsynaptic neuron decreases. Right? So I repeat that when nerve impulses are conducted repeatedly through an excitatory synapse, after some time, discharge of impulses from the postsynaptic neurons decreases. This is called fatigue of synaptic transmission. Now this fatigue of transmission is a protective phenomenon. It is a protective phenomenon against excessive neuronal excitability. It is a protective phenomenon against excessive neuronal excitability, and by the fatigue of synaptic transmission, an epileptic fit comes to an end. So by the fatigue of synaptic transmission, an epileptic fit, it comes to an end. You know about epilepsy. So during epileptic fit, there is excessive neuronal activity. Excessive neuronal activity during an epileptic fit. And by the fatigue of synaptic transmission, this epileptic fit, it comes to an end. So it comes to an end by the fatigue of the synaptic transmission. what is the mechanism of fatigue of synaptic transmission mechanism? The first mechanism important is exhaustion of stores of neurotransmitter in the synaptic node. Exhaustion of stores of neurotransmitter in the synaptic node. So neurotransmitters which is stored in synaptic nerve vesicles become exhausted because of repeated synaptic transmission, and this results into fatigue. The other mechanism is unresponsiveness of receptors on the postsynaptic membrane. Unresponsiveness of receptors on the postsynaptic neuron. So because of the repeated transmission to the synapse, the receptors on the postsynaptic membrane becomes progressively unresponsive. And this results into fatigue of the synaptic transmission. The next property of this transmission is summation. Summation is adding up of effect of stimuli on the postsynaptic neuron. Adding up of effect of stimuli or nerve impulses on the postsynaptic neuron. Keep in mind that one nerve impulse transmitted through a synapse is not able to excite the postsynaptic neuron. So keep in mind, one nerve impulse transmitted through a synapse is not able to excite the postsynaptic neuron. Excitation of this neuron occurs when there is summation. So there are two types of summation. One is temporal summation, and the other is spatial summation. So temporal summation and spatial summation. Now in temporal summation, nerve impulses are transmitted along the same number of synaptic nerves repeatedly. You understand? In temporal summation, nerve impulses are transmitted along the same number of synaptic nerves repeatedly. And the rate of repetition of these impulses should be such that the effect of previous impulse is still there, the next comes. So keep in mind, the rate of repetition of nerve impulses along the synaptic nerve should be such that the effect of nerve impulse is still there, the next comes. So this is the temporal summation. You see, this is the rate of, let's say, one stimulus, other stimulus, or one impulse, other impulse. So when the rate of repetition is such that the effect of the nerve impulse is still there, the next comes. And this is because of the repetition, there will be summation of effects of stimuli or nerve impulses, which results into excitation of the postsynaptic neuron. So same number of synaptic nerves or terminals are excited repeatedly. And there is such rate of repetition that the effect of nerve impulse is there, the next nerve impulse comes. And this is called the temporal summation. The second type of summation is spatial summation. Spatial summation. In spatial summation, increased number of synaptic nerves, or you say nerve impulses are transmitted along increased number of synaptic nerves simultaneously. You see, these are 1, 2, 3 synaptic nerves, and impulses are transmitted not simultaneously. So there won't be response, no action potential. And here, you see, in nerve impulses are transmitted along increased number of synaptic nerves, say 3 synaptic nerves, simultaneously, at the same time. And this results into response from the postsynaptic neuron, the action potential discharge from the postsynaptic neuron. Right? So this is the spatial summation, that nerve impulses are transmitted along increased number of synaptic nerves simultaneously. So the effects of these nerve impulses are added, summated, and this results into the excitation of the postsynaptic neuron, and this is the spatial summation. Right? So keep in mind, in temporal summation, impulses are conducted along the same number of synaptic nerves repeatedly, so that effects are added, and this results into the excitation of postsynaptic neuron. In spatial summation, nerve impulses are conducted along increased number of synaptic nerves simultaneously, so that the effects are added up in the postsynaptic neuron, and this results into excitation of the postsynaptic neuron. The next property of synaptic transmission is synaptic delay. Synaptic delay. There is a delay at each synapse, and that is called the synaptic delay. Why does this delay occur? This time is taken during synaptic transmission. Time is taken during synaptic transmission, and this time taken results into synaptic delay at each synapse. Synaptic delay, I told you, is due to synaptic transmission. Say, arrival of nerve impulse at synaptic nerve, release of neurotransmitter, binding up of the neurotransmitter with the receptors on the postsynaptic neuron. Then there is a influx of ions, other ions, production of EPSP, right? And then finally, the nerve impulse is generated from the postsynaptic neuron. So all these events take some time, and that is the time taken in synaptic transmission, that is the synaptic delay. Keep in mind, synaptic delay at each synapse is 0.5 millisecond. So 0.5 millisecond is synaptic delay at each synapse. At each synapse. Say if there is more number of synapses in the reflex arc, then there will be more synaptic delay. So more number of neurons or synapses in the reflex arc, there will be more number of more times taken in synaptic delay. At one synapse, it is 0.5 millisecond. 0.5 millisecond at one synapse. The next property of synaptic transmission is the effect of alkalosis. Alkalosis increases neuronal excitability. Alkalosis increases neuronal excitability. Acidosis decreases neuronal excitability. Acidosis decreases or depresses neuronal excitability. Hypoxia also depresses neuronal excitability. Hypoxia also depresses neuronal excitability. Say hypoxia for some seconds results into inexcitability of the neuron. Hypoxia for some seconds, it can result into unexcitability of the neuron. Then certain chemical substances can affect the neuronal excitability, Caffeine, theophylline. Caffeine is present in coffee in large quantity. Theophylline is present in tea. In tea, there is theophylline. So caffeine and theophylline increase neuronal excitability by decreasing the threshold of excitation. So caffeine in coffee, theophylline in tea increase neuronal excitability by decreasing the threshold of excitation. Strychnine, strychnine, strychnine increases neuronal excitability. Strychnine increases neuronal excitability by inhibiting action of inhibitory neurotransmitters in the spinal cord. So strychnine increases neuronal excitability by inhibiting inhibitory neurotransmitters in the spinal cord. Anesthetics, decreases neuronal excitability by increasing the threshold of excitation. Anesthetics depresses neuronal excitability by increasing the threshold of excitation. So this was about the effect of chemicals or drugs on neuronal excitability, and this was about the properties of synaptic transmission. Now, briefly about the functions of the spinal cord. Now, in the spinal cord, there is initial processing of the sensory information. Spinal cord contains ascending and descending tracts or pathways. Spinal cord contains ascending and descending tracts or pathways. Ascending tracts, sensory tracts; descending tracts, motor tracts or motor pathways. The other function is that spinal cord contains centers for neuronal centers or neuronal circuit, center and neuronal circuits for reflexes. Spinal cord contains center and neuronal circuits for the various reflexes. These reflexes, whose center or circuit is the spinal cord, these reflexes are involved in the movements, posture maintenance, withdrawal of parts of the body, local blood flow control, GIT movements, and many other reflexes. So central and neuronal circuits of various reflexes are present in spinal cord. These reflexes are involved in the movements, control of posture, withdrawal of parts of the body, local blood flow, GAT movements, and many other reflexes. Now I will start discussion on reflex action. Reflex action. What is reflex action? An automatic response to a stimulus without involvement of the will or consciousness. Right? So this is the reflex action. An automatic response to a stimulus without involving the will or consciousness. So an automatic response to a stimulus without involving the will or consciousness. You see, this man is walking barefooted. On the ground there is painful object. This painful object or stimulus strikes his foot. And what change you see in the foot? The leg is flexed and foot is withdrawn. The foot is flexed and withdrawn. This is a reflex response. Now in this response, no involvement of the will or consciousness. Right? So this is a reflex action, an automatic response to a stimulus without involving the will or consciousness. Now what is the purpose of reflex action? What is the purpose of reflex action? Its purpose is to have quick response, and to save time. To have quick response and to save time. It also has a protective value. It also has a protective value. So this painful object touches the foot and the man starts thinking whether to withdraw the foot from this painful stimulus or not. Damage would occur. But without involving the will or consciousness, the foot is automatically withdrawn from the painful stimulus. So this is a reflex action. You must have studied the light reflex. You show bright light to the eye, pupil is constricted. Without your knowledge, without your will. So again, this is a protective action, so that the bright light may not damage the retina. Right? So reflex action is an automatic response to a stimulus without involving the will or consciousness. The purpose is to have quick response to save time. It also have got protective value. It prevents the tissue damage. Reflex action involves activation of skeletal muscle, or smooth muscle, or cardiac muscle, or glands. It involves activation of the skeletal muscle, smooth muscle, cardiac muscle, and the glands. Reflex action requires a particular organization. Reflex action requires a particular organization which is called reflex arc. So reflex action requires a particular organization, the reflex arc. There are 5 components of the reflex arc. There are 5 components of the reflex arc. What are these 5 components? Receptor, sensory or afferent neuron, the center, efferent neuron, and then the target cell or the effector. These are the 5 components of the reflex arc. Receptor. The receptor responds to stimuli. And generates impulses. The receptor responds to stimuli and generate impulses. These impulses from receptors are transmitted along the sensory neuron to spinal cord or to central nervous system or to center. So impulses from receptor are transmitted by the sensory neuron, afferent neuron to the center. This is the center. Center is in the central nervous system. Center is in the central nervous system, the spinal cord or the brain. Center is an integrating center. Center is the integrating center, which is there always in the central nervous system, the spinal cord or the brain. And then the next component of the reflex arc is efferent neuron, motor neuron, which carries impulses from the center to the effector. So efferent neuron or motor neuron carries impulses from the center to the effector or the target cell. And the target cell or effector, it responds. So the effector or target cell, it responds. And response occurs. So these are the 5 components of the reflex arc. And keep in mind, for reflex action, the reflex arc must be intact. So intact reflex arc is essential for the reflex action. If reflex arc is broken, discontinued, then there won't be reflex action. There won't be reflex action when this reflex arc is broken or discontinued. Reflexes can be classified in different ways. One way is depending upon the number of synapses in the center. We classify reflexes depending upon the number of synapses in the center into monosynaptic, disynaptic, and then polysynaptic. So monosynaptic, disynaptic, and then poly or multisynaptic. Monosynaptic. Now in the center, only one synapse. One synapse between the afferent and efferent neuron. So one synapse between the afferent and efferent neuron, and this reflex is monosynaptic. Now if between afferent and efferent neurons, one interneuron is present, between afferent and efferent neuron, it is a disynaptic reflex. And if more than one interneuron is present between the afferent and efferent neuron, it is called multisynaptic or polysynaptic reflex. If more than one interneuron is present between the afferent and the efferent neuron, then the reflex is polysynaptic or multisynaptic. So I've told you about the reflex which is monosynaptic, then disynaptic, and then multi or polysynaptic. We can also classify reflexes into two types. One type is inborn or unconditioned reflexes. Inborn or unconditioned reflexes. The second type is acquired or conditioned reflex. Acquired or conditioned reflex. So inborn or unconditioned, and the second type is acquired or conditioned reflex. Now inborn or unconditioned, which are present at birth. Say knee jerk, light reflex, knee jerk and light reflex. Salivation when something is introduced into the mouth. Salivation when something is introduced into the mouth. So these reflexes are inborn, present at birth. The second type is acquired or conditioned. These are not present at birth. These are developed in response to a conditioned stimulus. These are developed in response to a conditioned stimulus with the help of an unconditioned stimulus. So these are developed in response to a conditioned stimulus with the help of an unconditioned stimulus. I give the example of the historical experiment of Pavlov. Pavlov, P-A-V-L-O-V. When Pavlov experiment carried on animals, dogs, the animal was trained that first a bell was rung and then food was served. A bell was rung and then food was served, and the effect on the salivary secretion was noted. Was noted. So a bell was rung, food was served. When food was served, there was salivary secretion. Now, after many times repetition, bell was rung, food was not served. Bell was rung, but food was not served. Still there was salivary secretion. Salivary secretion is an unconditioned reflex, and it was accompanied by a reflex that was conditioned, that was ringing of bell. Right? So we developed this acquired reflex in response to a stimulus which was conditioned, ringing the bell, with the help of a stimulus which was unconditioned, that is salivation, when something was introduced into the mouth. So this was the acquired reflex or conditioned reflex. We can classify reflexes in another way, and that is the clinical classification of the reflexes. Clinical classification of the reflexes. We classify into superficial, deep, and pathological. So clinically, we classify reflexes into superficial, deep, and pathological. Superficial reflexes, receptors are present in the superficial tissue. Receptors are present in the superficial tissue, skin or mucous membrane. Skin or mucous membrane. Say, superficial abdominal reflex, superficial abdominal reflex, corneal reflex, conjunctival reflex, plantar reflex, plantar reflex. So these are the examples of superficial reflexes. Now you come to deep reflexes. For example, tendon jerks. Receptors are in the deeper tissues. Receptors are in the deeper tissues, say in the muscle, maybe tendons, right? Say knee jerk, bicep jerk, knee jerk, bicep jerk, triceps, ankle, supinator, jaw jerk. So these are the deep reflexes or tendon jerks. Knee, biceps, triceps, ankle, supinator, and jaw jerks. Then there are pathological reflexes, and these include Babinski's sign. Babinski's sign present in the upper motor neuron region. So Babinski's sign is present in the upper motor neuron region. And then clonus. So clonus is an abnormal type of reflex present also in the upper motor neuron region. So Babinski's sign and clonus are present in the upper motor neuron region. So this was about how the reflexes are classified. Right? So this was about today. Thank you very much.